6.2 is the other function that we'll be working with in Unit 6, and they are called the logarithmic functions. Goofy name, and these sometimes really trip people out just because they're so unusual and so different from what we're used to seeing. It turns out, though, logarithmic functions are the inverse of exponential functions. And remember back in a couple of units ago when we talked about inverses, I said inverses cancel each other out or they undo each other. They're like opposites. So logarithmic and exponential functions are inverses. So the first objective today is just kind of going back and forth between the two. And then the last focus will be, the last focus will just be evaluating them and graphing them and just getting used to this weird type of function. So, what are these things? Well, before we look at what logarithmic functions are, I want to stress again what I just brought up. Exponential and logarithmic functions are inverses of each other. And what I mean by that is you can think of it as they undo each other, or they cancel each other out. Okay, so what? That still doesn't make any sense. Well, what I want you to think is if I gave you this, and I said, hey, what is that answer? You would tell me, well, 5 squared is 25. And I'd say, perfect. That's an exponential setup. What they needed in the math world was a way to go backwards without having to use 50 million words to describe what they were doing. So they came up with something called a logarithm. And when it's used in math, it's abbreviated log. And you would see something like this. And what this represents, we are literally going backwards. So if I gave you this log problem and I said, what is this answer? You have to first understand, what is this even asking? What this is asking, this is like a sub 5. It's asking 5 to what power is 25? 5 to what power is 25? So the answer would be 2. So whenever you answer a logarithm, your answer is an exponent. You're going backwards. You're telling me what was the exponent used to do that. So it's the exact opposite of an exponential setup. So if we're going back and forth between the two, if I had this log form, so log and then a little base b, x equals y, so if I use a lot of variables there, the exponential form of this, it's pretty easy to go back and forth between the two. The base number b will be the base. The exponent is the answer to the log, so the y is the exponent, and then x. Some people, in order to convert back and forth, some people do, it's kind of like an arrow. They'll start at b, arrow around, end at x, meaning it would be b to the y equals x. But the big thing to remember, whenever you answer a logarithm, the answer is an exponent. I can't stress that enough. So again, if you wanted to write something down, if I had this, let's say I had log base 2 and then 8. What that is asking, that's asking 2 to what power is 8. That's what that is asking you to do. So the answer to that log would be 3, because 2 cubed is 8. So let's first look. The first few homework problems will just be getting used to this new notation and jumping back and forth between exponential and logarithmic. So it says, write the equation in exponential form. So this first guy, I'm going to write it like this first. I'm just going to flip-flop it. So if I want to write that in exponential form, if the arrow trick helps, do it. So the base number, 5, is the base. And now I need the exponent. Well, the answer to the log was the exponent, so 2 equals x. Done. That's all I want to do. I just want to rewrite it in the other form. Let's try the next one. I'm going to write it first the other way. Okay, so if I rewrite it, it would be b cubed equals 64. That's the exponential form. And the last one, if we rewrite that in exponential form, my base of 3 raised to the y equals 7. Done. Okay, what if we go the other way? I give you the exponential form and I want it written in log form. Well, we'll start with log. The base is 12, so that's going to be my little subscript. And now the question is, where do I put the remaining items? Well, I know, again, if you want to do a little arrow trick, the x is going to be next. And I know the answer to it has to be the 2. Why do I know that? Because the answer to a log has to be an exponent. Since the 2 was the exponent, that is what it's going to be equal to. Let's try the next one. So log and a base of b, because that was the base, and then the 8, and the answer to it should be the exponent. That was 3. Next one, log base e. Remember, e was 2.72. It's a number. And then 9 equals my exponent of y. So we just got to get used to going back and forth between the notation. And you might say, what is the purpose of going back and forth? Well, when we get to solving these, some equations are easier to solve in exponential form, and some equations are easier to work with in logarithmic form. It just depends on what we're dealing with. So it's good to know how to go back and forth. Okay, this next set will be a big section of the test, evaluating logarithms, finding me the answer. So let's see if we can figure this out. This first guy, log base 3 of 81, they want the answer to that. So this is asking 3 to what power is 81? That's what it wants me to do. 3 to what gives me 81? That's what I want to find. So you could try 3 squared, but 3 squared is 9. Maybe 3 cubed? Well, that's 27. What about 3 to the 4th? 3 to the 4th is 81. So the answer to this is 4. The answers are the exponents that I would have to use. Next one, log base 5 of square root of 5. Now it's been a while since we've done this, but if radicals are involved, we want to rewrite this. So right now this is a square root, so it's like there's a 2 there. Let's rewrite it as 5 raised, and now if I rewrite it as an exponent, it would be 1/2, because remember, when you rewrite it, the exponent outside is the top number, and the radical, the root, is the bottom number. So now this is asking my base of 5. 5 to what power is 5 to the half? Well, that's easy to see. X, it has to be 1/2. 5 to the half is 5 to the half. Let's look at the next one. This is asking 7 to what power gives me 1/49. A common mistake on this one is to say, well, it's 2 because 7 squared is 49. But the 49 is in the denominator. How would I get it to move down? Turns out the answer is -2, because 7 to the -2 would move it to the denominator, and that's how I would get 1 over 49. Next one, 2 to what power is 2? Well, this 2 technically has an exponent of 1, so it has to be 1. Next one, 8 to what power is 512? Well, you might say, I wonder if it's 8 squared. Well, 8 squared is 64. What about 8 cubed? Yes. It turns out that 8 cubed is 512. Next one, 4 to what power is 4 to the 3.2? Well, that's easy to see. It would have to be 3.2. Next one, 2 to what power is 1 over 32? Well, 2 squared is 4. 2 to the third is 8. 2 to the fourth, oh, that's 16. 2 to the fifth, yes, that's 32. But if you have 5, it's wrong. It needs to be a -5 because that's how the 32 ends up in the denominator. Okay, so it turns out when we're evaluating logarithms, we have some simplifying properties that will actually help speed up the process. So if you're taking the log, I don't care what the base number is. If there is a 1 sitting after the log, the answer is always going to be 0. Why? Well, think about it. If I had something like log base, I'll do 8 of 1. That is asking 8 to what power is 1? Well, we know anything to the 0 power is 1. So that's why if there is a 1 sitting here, I could care less what the base number is. The answer is going to be 0. Next one, what happens if these two numbers are the exact same? The answer is 1. Why is that? Well, this was asking b to what power is b? Well, there's a 1 sitting there, so it has to be 1, and we actually did one like that right here. You can also think of it as, some people like to think of it this way, as it's like they cancel and I'm left with the exponent. So in theory, look at this next guy. If they're the same but the exponent was something other than 1, well, whatever that exponent is will be the answer, because it's like, think of it as they cancel. We did one like that right here. See how the answer was the 3.2. And what about, ooh, look at this one. This one looks really nasty. Well, the answer is x. And the reason why this one works, if these are the same base, since exponential and logarithmic functions are inverses, when I put one inside the other, they cancel out and I'm left with just whatever that x was. Now, what if they do something like this? Log of 35. What if there's no base number written in? Well, if there's no base number written in, then the logarithm is assumed to be a base of 10. Now, on your calculator, you should see a log button. However, the log button on your calculator can only be used if it's base 10. That's what that button is for. So let's try some more of these just because they're a big deal and I want to make sure that we have them down. So this one, log base 5 of 125. So it's asking 5 to what power is 125? Well, 5 squared is 25. What's 5 cubed? 5 cubed is 125. So this answer is 3. Next one, 9 to what power is 81? The answer should be 2. Next one, notice how the bases match. If the bases match, they cancel out, I'm left with 1. Next one, the bases match. They cancel out, I'm left with 4.7. Next one, the bases match, they cancel out, and technically the exponent was 1, so I'm left with 1. Next one, this is asking 3 to what power is 1? Well, it's 0. Anything to the 0 power is 1. Next one, notice how there's no base number denoted. If you want, we're going to write in a 10. It's a 10 if there's no number there. So this is asking 10 to what power gives me a decimal out? Well, if I'm getting a decimal out, that means this 10 would have to move to the denominator. So what if I try like 10 to the negative 1? Well, that would be the same as 1 over 10. But 1 over 10 is 0.1. I need 0.001. What about 10 to the negative 2? Well, that would be 1 over 10 squared, which is 1 over 100, but that's 0.01. It turns out this answer is negative 3. Okay, what about the next one? Notice this log up here does not have a base written in, so I'm going to write in base 10. Oh, hey, they have the same base, so they cancel, and I'm left with 5. Next one, no base written in, so it's 10. So this is asking 10 to what power is 26? This one you need a calculator on. This is a decimal. So this is one where I would just type in my calculator log 26. So see if you can do this. Hit the log button and then just do 26. And it's going to give you a decimal. Let's go 2 decimal places. So this decimal answer with rounding would be 1.42. Does this answer make sense? Let's see. 10 to the first would be 10, but 10 squared is 100, so it makes sense that this answer is between 1 and 2, because 10 to the first was not enough to get to 26, but 10 squared was way too much. What about the next one? I'd like you to enter this one in your calculator. So hit the log button and then do negative 5. And your calculator should say error. It doesn't like this. It's asking 10 to what power is negative 5? If you are trying to take the log of a negative number, it's not possible. So we're going to say does not exist. DNE, not possible. Why? There is no number that I can raise something to and get a negative number out. You might say, oh, that's easy, just use a negative exponent. Well, if I use a negative exponent, that doesn't turn the answer negative, that just flips it. There is no exponent you can raise something to and turn the answer negative. It can't happen. So that's why logs don't like that. They can't find the exponent. There isn't one. Next one. Log base 6 of 1/6. Well, I think I'm going to make this easier, I'm going to bring the 6 up first. But it would now be to the negative 1, right? Because I moved it, it changes the sign of the exponent. And the reason why I moved it is now, hey, they're the same base, they cancel out. I'm left with negative 1. What about the next one? Well, there's a radical. I don't like that radical, so let's rewrite it first. That's the same as 3 to the 1/2. I'm going to bring it up. So now it's 3 to the negative 1/2. And the reason why I did that is my bases match, so they're canceling. And my exponent that's left is negative 1/2. What about the next guy? 81 to what power is 9? How do I turn 81 into 9? Well, the only way to turn 81 into 9 would be to square root it. The square root of 81 is 9. What exponent represents a square root? 1/2. So this answer is 1/2 because 81 to the 1/2 is the same thing as square root 81, which is 9. The other character that we will run into is something called natural logs. These are still logarithms, but they are a specific type of logarithm. They are a log with a base of e. So rather than seeing this, if the log has a base of e in the math world, it gets written this way. I will never write ln this way just because that looks too much like a 1, so I'll use a cursive L. I don't care if you do that or not. It's just what I do so I don't get confused. Oh, sorry. And it's not e. Geez. It's natural log 3. The natural log replaces the log base e. So if you see a problem with ln, it's a logarithm, but you can automatically know its base is an e. It's understood that it's e. So let's just practice evaluating these. So evaluate each logarithm. The natural log of e to the 0.73. Well, I know its base is e because it's a natural log. And hey, it's the same property. If the base and the number match, they cancel out, and I'm left with whatever was left. So this next one, since it's natural log, I know the base is e. So this is asking e to what power is 4. We're going to need the calculator. So in your calculator, I would just simply, you should have an ln button. So hit the ln button and then type 4. And it's going to give you a decimal. And that decimal, let's go 2 decimal places. The answer would be 1.39. Does that make sense? It's saying e to the 1.39 is 4. Well, remember, e is roughly 2.7. So yes, this is a reasonable answer. Next one, e raised to the ln of 6. Let's write in the base number of e. Hey, they're both the same, so they cancel. And I'm left with what's left, the 6. And the last one, natural log of -4. Go ahead and type this one into the calculator. Natural log -4. You should get an error. Why? Logs don't like negatives. There is no exponent I can raise something to and get a negative answer out. It's not possible. Okay, the last thing I want to focus on today are the graphs of logs. And if you were able to graph the exponential functions from last time, graphing logs is also very similar. So there are 2 types of logarithmic functions, growth and decay, just like last time. Let's look at the growth ones first. So if it's a growth, it'll be in this form. Log base b x. And what makes it a growth, b will be greater than 1. My base will be greater than 1. That's what makes it a growth. So what you end up seeing when you graph these, since they are the exact opposite of exponential functions, they're the inverse. Instead of having a horizontal asymptote, they will have a vertical asymptote at x equals 0. They're the exact opposite. And last time, they always had a y-intercept of 1. Because these are the inverse of exponential functions, they will have an x-intercept of 1. And then what you'll see happen is the graph will grow. So literally the exact opposite of exponential functions. So if I were, I just want to quick talk about the domain and range. Last time it was always the domain that was -infinity to infinity. This time it's going to be the range that's always -infinity to infinity because it's the inverse. Now, if I do the domain, how far left and how far right? Well, the furthest left this graph gets to go is to 0, but then it keeps going to the right. So again, it's like the exact opposite of the exponential function. The decay graph will be in the same setup. Except what makes it a decay is the base number will be less than 1. So when I graph it, I'm going to have my vertical asymptote at x equals 0. I will still have an x-intercept of 1, but this time the graph is going to fall. And the domain and range would be the same. I want to show you something trippy that happens before we do the next example, because I don't think a lot of people realize this. So if I looked at a big graph here, in red, this is an exponential graph, exponential, which is what we did last time. In blue, is the log graph. Since they are inverses of each other, if you look back at the unit where we talked about inverses, I said when they're graphed, they are always a reflection over the line y equals x. And that is exactly what's happening here. Because they are inverses, their graphs are a mirror image. That will always, always, always happen. I just want you to see that connection. The same thing would happen with the decay graphs. Okay, so it's not a coincidence. There is a reason these graphs look the way they look. So let's try an example. Graph the function, and then we're going to describe all the characteristics. We're not doing end behavior. So just like what we did last time, let's first decide, is this going to be growth or decay? If I look at the base number of 3, since it's bigger than 1, this is a growth. So since it's not moving left, right, up, or down, I don't have any transformations, I know my asymptote will be right through 0. So it's through x equals 0, so I'm going to write that down. I know that I will have an x-intercept of 1, but I'm not going to have a y-intercept this time. I'm not going to touch that vertical asymptote. We can draw in the growth graph. It's going to grow as time goes on. And now let's answer the domain and range. So I know the range is always going to be negative infinity to infinity because it's always going to go down and always going to go up. But the domain, how far left do I go? Well, I get closer and closer and closer to 0, but I don't pass that 0 line. And then I keep going to the right. So there would be my domain. And it's done. Let's try the next one. Well, is this decay or growth? Since my base is smaller than 1, I know this is going to end up looking like a decay graph. Since there aren't any transformations on this, I know I'm still going to be having a vertical asymptote through x equals 0. My x-intercept will always be 1 to the right of it. Kind of like last time, the y-intercept was always 1 above. So I'm going to draw in, make sure when you draw in the graph, we are decaying. And now let's answer. I know my range. My domain, I still get close and close to 0, but I keep going to the right forever. And the last things left, I just want to make sure we still are reviewing the transformations. So describe the transformations if this time log x is the parent function. So on this first one, they have a plus 4. See how the plus 4 is inside the parentheses with the x. So since it's inside with the x, this is going to be either left or right. And remember, it's a liar. So this graph would actually be moved left 4. Okay, the next one. I have two transformations. Let's do the minus 2 first. Since it's inside with the x, this is going to either be left or right, and it's a liar. So we're going to go right 2. And now there's a 3 multiplied out front. So remember, when things are multiplied, that's either going to be the stretch or shrink. Since it's multiplied out front, it's vertical. And since 3 is bigger than 1, it is a vertical stretch of 3. Okay, and the last one, there are two transformations. We have this minus 5, and then we also have a negative out front. So the minus 5, a lot of people will tell me that means right 5. But it's not with the x. The minus 5 is out back. So that actually means down 5. If they wanted it with the x, they would have written it like this. They will use parentheses to indicate if it's inside with the x. If they don't, it's out back. And then the negative out front, that is an x-axis reflection. The whole graph would go upside down. Okay, and the last one, find the domain of this function. Let's see if we can do it without even seeing the graph. So first, I would identify what is this transformation doing? Well, that's left 3. So just think about it. On the original graph, if I look at the original graph, notice how the domain was 0 to infinity if it hadn't have moved. But this graph is moving left 3. So the domain will now be negative 3 to infinity because literally everything has moved left 3. So it was at 0, now it's at negative 3. And that's it. That's the domain. The range would still be negative infinity to infinity.